Hello, everyone. Welcome to CS6476 office hours. This is probably not a surprise to anyone here, but we're going to wait 5 minutes to get started just to let people show up and join the chat, either the video chat or the YouTube. Looking forward to one last Wednesday office hours. Okay, good evening, everyone. Thank you all for coming to Wednesday Computer Vision office hours. Before we get to the technical part of office hours, I've got a few logistical points. First, office hours is being recorded to be shared with the class later. You can ask a question via text or via video chat if you're in the Google Hangout. But in either case, I will probably repeat your question, and that will be recorded for the entire class to view. This week, we've only got a few questions, so I think it's going to be roughly about 20 minutes of me addressing questions that I was able to prepare material for, and then we'll open things up for general discussion. So with that, let's get started. All right, so today in time for me to prepare material, I only got 2 questions that I could work with and have something ready in time. The first was a request to go over the simple stereo correspondence algorithm, and the student was concerned that they weren't getting great results with their implementation, even though it seemed correct. And so I'll do that. I'll talk a bit through the basic algorithm, and I'll also show what kind of results you can expect with such a basic algorithm that really end up not being too great. And then there was another question that I thought was interesting. It had 2 parts. The first is, how do we know if a paper represents new or cutting-edge techniques? So I've got one fluffy slide where I talk about how I do research and decide if a paper is important. And then I'll also talk a bit about the enhanced roadside detection as an example and try and show a few more interesting papers related to that project. Once we've gone through those 2 things, I'll open the floor up for general questions. I'll also try and hit verbally all of the questions that showed up in the office hours thread, but I didn't have time to make slides for. So here's today's agenda. I've already gone over this verbally, so I'm not going to bore you with it again. Let's dive right into simple stereo. So for those of you who aren't doing the stereo project, a tiniest bit of background. In the stereo project, we ask students to do 2 things. One is implement a simple stereo matching algorithm. And the second is to implement a more advanced algorithm that does some kind of energy minimization or graph cuts. So all of this office hours is just about the simple stereo algorithm, which is quite straightforward and provides a baseline that students can compare their results on the more sophisticated algorithm to. So the goal of stereo, or in the stereo project, is to generate disparity images. And so what's a disparity image mean? Well, you have an image from a left camera and from a right camera. I might have that backwards, but you have images from 2 cameras. And you take both images and you pop out these disparity images. And a disparity image is how much an object moves or a pixel moves in between images. You can see this spray bottle of stain remover moves a fairly large distance from image 1 to image 2. And so it's fairly bright. And these clothing in the very front here moves even farther, so they're the brightest in the disparity images. And we have 2 disparity images because one is, if I look for a pixel in this image, how far did it move in this image? And then you have vice versa. And so they're just 2 different viewpoints. And the reason we care about disparity is if you have disparity and you know how far apart your 2 cameras are, you can calculate depth through some relatively simple trigonometry. So this is sort of the goal of all stereo algorithms. And we're going to talk through a really simple algorithm, which is what you just might think of naively if you wanted to know how to solve this. So the key idea, and this is here just showing images, is we want to find how far things move. And we know from our long sojourn into projective geometry about epipolar lines. So we know that objects will have moved along an epipolar line. In this case, you can think of the epipolar lines as just being horizontal lines because we've set up our cameras cleverly. And along this epipolar line, we find a little patch of the image in one in one of our stereo images. And then we hunt along the epipolar line in the second image to find the same patch or a point in the image that's most similar. And so in this case is right here. We take this distance d and use that to set the value of the pixel in the disparity image. So the value of this pixel is proportional to this distance along the epipolar line. So that's the algorithm in images. And if we want to put that in words, it's for every point in the left image, you take a little patch, and then you search along the horizontal line in the right image, and that line is defined by having the same y coordinate as the point we're working with. And we find the best matching patch, which is going to have a different x coordinate. So with our little green square example, this is our point xy where my mouse cursor is hovering. And then we search along this horizontal line here to find the best match, which is the same y coordinate, but a new x coordinate. And then we set the intensity of the pixel in our disparity image to be that motion, the magnitude of that motion. And we're glossing over a whole lot of detail here. In particular, horizontal lines only work when your camera axes are well set up and your epipolar lines are horizontal. In a more general case, you search along an epipolar line. And I also want to just pause here for a moment that you have to be clever with OpenCV and NumPy if you want to do this search in any reasonable amount of time. Back when this used to be a problem set, we'd get lots and lots of submissions that took hours and hours to run, because you can imagine if you have a loop for every pixel in the left image, for every pixel along the line in the right image, you're starting to get very large loops very quickly. So you do have to think about using NumPy and NumPy indexing to do these calculations efficiently. So what can you get out of this? It turns out you can get something that looks suggestive but not great. So on the left here is the ground truth Middlebury image. So this is what we're aiming to get. And on the right is what you get from this sort of simple stereo algorithm. And this has actually been tuned a fair amount. You can get certain objects to pop out more or less with different amounts of tuning. And so you can see, here's the spray bottle and it's roughly the right color. And you can see the laundry here is roughly the right color and gets darker. And the basket is darker. And you can even see some of these little lines. But this is an extremely messy image. It's got no idea what to do in areas that were occluded in the original image. And it's got lots and lots of messiness and noise. So this is about what you can expect to get out of simple stereo on the stereo project. And the goal of asking you to implement a more sophisticated algorithm is you can get something that looks much more like the ground truth images. And the last comment I have about stereo is, for this particular project, it makes a lot of sense to set up a test bed so you can have some sense if your algorithms are working correctly. And the way to make a test bed is to create an image that's got a nice random pattern, so there's no repetition in this image, and then put on top of it a cut from a second image with a different random pattern, possibly a little darker, and move that cut slightly to the left in a different image. And then you can see, am I getting a uniform 2-pixel displacement over this entire square? This sort of generating a very synthetic test image like this helps you get away from some of the messiness in the simple stereo algorithm and gives you something you can be sure your algorithm is working correctly on before you jump right to the Middlebury data set where you get some messiness right away. And that's really all I have to say about stereo. Do we have any questions about that before we move on to analyzing papers and some papers for road sign detection? All right, seeing no questions, I'll jump right into papers. I'm going to try and keep this relatively brief because I don't want to be your high school librarian lecturing on how to do research. This is just my personal perspective. It's what works for me. I tried to think about how I look at papers and what my process is. So to me, the words state of the art mean recent, which typically means sort of less than 7 or 8 years old. This varies depending on field. Deep learning is a field that's moving very quickly, so that might be less than 2 to 3 years old for deep learning. Road sign detection seems to move a little bit more slowly. I think 7 to 8 is about right for that field. But in general, you're looking for something within the past decade, preferably within the past 5 years, maybe even more recent. And you're also looking for excellent results. How do you know if a paper's got excellent results? Well, one, hopefully they've used a widely accepted benchmark to test their algorithm that many other people have tested algorithms against, and you want to have some sense of what results other people are getting on this benchmark compared to the results that are being presented in this paper. The other thing is the paper's writing quality and use of standard terms in the industry should be generally excellent and enough to convince you that that they're applying their algorithm correctly to the data set and interpreting data set results correctly. So how do I find papers that I think are state of the art? I'm a big fan of Google Scholar. And if I'm looking at a completely new topic that I don't have much experience with, or I don't know what the important papers are, the first thing I'll Google is topic name survey, so road sign detection survey, and try and find a survey paper that's going to list a bunch of different techniques, how they perform, hopefully do a bunch of benchmarking between different techniques. And so that gives me a high-level view of the field. And the other topic I'll plug into Google Scholar fairly early on is the name of some benchmark, often that I found in the survey paper. For example, the German traffic sign detection benchmark. And that's very useful to find the original paper, because all of the papers that use it will cite it. And you can use these citations to sort of build a web and see how papers are connected within the field. Google Scholar offers two features. One is you can see all the papers that cite a given paper, and they'll also give you articles they think are related to a given paper. And both of these help you sort of branch out from these few initial papers you found to overall build a sense of the field and a sense of what is the state of the art. And I think I'm going to leave this discussion here. If it works for you and this method makes sense, great. If not, feel free to ignore me. Lots of people have different approaches to doing research. And because the question asked, I did take a look at what are, I personally feel, the important survey papers in road sign detection. And here are two of them. One I've linked to earlier, this first one. And I actually found this second one earlier this week, and I like it because it also does some benchmarking. And you'll actually see a number of topics discussed in this class showing up in the solutions they benchmark, including Viola-Jones, Hoff-based classifiers, and a histogram of gradients-based classifiers. So these two are very good papers to look at if you're trying to get ideas for what to implement. And then I also pulled out two data set papers. One is this German traffic sign detection benchmark, which has been around for a while, but a lot of the very interesting papers in the field from about 2011 through 2015 rely on this data set. So by looking at this paper and seeing what cites it, you can easily branch out and find other papers that get good results. And there's also this 2015 paper that presents some US traffic sign database, which is interesting for the same reasons. And that's what I have in terms of prepared topics today. There are a lot of questions that came in within the last hour or so from on the Piazza forum. So I think I'll take a combination now of live questions, and if the live questions aren't coming in, I'll start pulling them from the Piazza thread. All right, so first Piazza-based question that I have is, can I provide more guidance for the convolutional neural networks project? The instructions tell us to use VGG for classification. What about segmentation? Can we use another CNN? How about some hints? So I'm going to be completely honest that deep learning is not my specialty. I've dabbled in it. I've set up a few networks, but I don't consider myself an expert, and I don't want to sell myself as an expert to you guys. Some of the other TAs in this class are bona fide experts in the topic. I would encourage you, if you're working on that topic, to pop into Naveen's office hours on Friday. I know that he has published research in neural networks, and I think particularly generative adversarial networks. But he probably can give you much better hints and advice than I can. So with that massive disclaimer, here is the advice I'd give. I'd start by watching the lectures that Bobbitt gives on segmentation, which gives you a pretty decent overview on how segmentation is done classically, not using neural networks. I'd also do some Googling for topics like SegNet, which is, I think, pretty much the standard neural network architecture that's used for segmentation. If I'm remembering correctly, it uses the VGG network layers as an input encoder, and then has a set of layers that re-expand out into a segmented image. But it's been a while since I looked into that, so I think the main word here is Google SegNet, SEGNET, for information about how people are doing segmentation with neural networks. All right, next Piazza question is, for enhanced augmented reality, I'm having a difficult time understanding the second paragraph in the requirements. For this topic, your report should contain runtime benchmarking of your code and a discussion of the processing power required to run your code in real time. Your code should be optimized to run in as close to real time as possible. This replaces the requirement to benchmark your algorithms against a public imagery database. Yeah, so this is a lot of words to try and say something that I hope isn't too confusing. So the great challenge in augmented reality is what people want to do very much is have a cell phone or the Google glasses, and in real time, as you walk around, have objects appear. So that's sort of the key challenge in augmented reality. And so we'd like you to keep that challenge in mind as you implement your algorithm. In particular, if you have a, let's say, 10-second segment of video, your algorithm should take no more than 10 seconds to process it. At least that's the goal. And your video's at 30 frames per second, so that means you have about 33 milliseconds to process each frame. You don't necessarily have to meet that goal, but we want you to talk about how your code compares to that speed goal and what it would take to meet that speed goal. It's a real challenge in the field getting these fairly complex computer vision algorithms to run on the minimal hardware you find in a smartphone or that you can wear as glasses. All right, I'm going to do the last Piazza question, and then I'll jump to, I'm starting to see some questions roll in on the Google chat. So the last Piazza question I have is, can I give some instructions for the augmented reality or on what would be the best methods to find clear areas? Instead of Harris corners, should we find specific points and consider them as our markers? and can I give some instructions? So I can give a fairly high-level explanation of each of the steps. The first is finding clear areas, and this is a problem that you can make very easy or make very difficult. It is not the main focus of the enhanced augmented reality. So something very, very simple you can do is you can ask yourself what makes an area in an image clear, and that's probably going to involve something with edges or corners or uniformity, and just try and pick out a clear area and use that for the beginning of your algorithm. Put your image there, and then as the camera moves, you're tracking camera motion, you keep your image in one spot. You can also try and get more sophisticated for that initial placement of the image and try and find a flat surface, and you'd want to look into algorithms for detecting planes in images. That's typically based on motion. You can see which motion which points motion are consistent with those points being on a plane. Bobek talks about this a bit in the lectures on optic flow. So then, but once you've got your image projected into the video, into the first frame of the video, you're going to want to anchor it to certain points in the image and say, this is the position of my object relative to other points in the image that are actual real objects in the scene. And then you'll track those points as the camera moves, and you'll remember where they are even when they're out of the image. And so you aren't necessarily using those points as markers per se, but you're using them to keep track of what's happening in the image. And I think that's the best explanation I can give off the cuff. If that's ended up being confusing, feel free to make a post in Piazza that I can get to within the next day or two after I've given it some thought. All right. The next question I see is, I'm doing enhanced augmented reality, and I believe that's the only one that was not given some sample data to work on. Is there some videos that you recommend getting started with? Yeah, two recommendations. One is walk around your house with a camera or a webcam and use that video to start with. In particular, find a room that has some blank space on one of the walls and swing a camera around, and that can give you a good starter video. The other starter video example that I think people could work with to get a fast start on the algorithm is just take the problem set 3 videos, pretend you have no idea that there are markers in those videos, i.e. that they're nothing special, and see if you can work with those and that it behaves well. And that's, I think, actually the easiest way to get started on the problem. All right, another question is, for global stereo correspondence, I've been looking into semi-global matching, which was proposed in 2005. Would this still be considered a good topic, even though it's a bit older? I don't want to, in office hours, say yes or no to any specific algorithm. So I'm going to encourage you to make a Piazza post on the stereo correspondence page for the specific algorithm question. I will say it's okay if your technique is a little bit older. We don't need you to implement, the latest technique that appeared in 2017. We just need you to compare the technique you've implemented to state of the art, and your technique has to meet the requirements in the problem set description. So is it an energy minimization technique or a graph cut space technique? If it is, that's a technique you can use, and you'll need to compare it to what people are doing now in your report. I have a question about grading. For grading, will our EAR project be run as is, or will you be inputting an image or testing for general robustness in any way? I'm not sure I want to say too much about this, but we will be certainly looking at your algorithm to decide if it if it could be robust. If you say, the first step in my algorithm is to look for the corner of the potted plant in my living room that's in this video, then we'll know it's not robust right off the bat. I don't know, and even if I did know, I don't think I could say if we'll have any necessary or any specific grading case for robustness. But we do want your algorithms to be robust and be operative in a general scene, not fine-tuned to any specific object in your test videos. All right, I'm not seeing too many more questions, so unless I see more roll in the next few minutes, we'll call office hours early. Just to give people some sense of, great, someone's writing up a question and getting the words straight. Well, then I certainly won't leave before we get that one. Will we wait? I want to say that just give a sense of my schedule for the next few weeks. I'll certainly be active on Piazza, but there won't be office hours next week, the 22nd. That's the day before Thanksgiving here in the United States. And so I just can't commit to a 9 p.m. office hours that day. I will be having some form of office hours on the 29th. By that time, everybody's probably neck deep in their projects and knows more about their specific case than I do. So rather than have that office hours be devoted to the final project, I think I'm going to try and do some form of final exam review session in which I pretend to be Professor Bobek, but talk really, really fast so we can cover the whole semester in 1 or 2 hours and talk about what's important, what needs to be reviewed, and what some of the core concepts and algorithms from the course are. And that takes us through pretty much the end of the course. Yeah, okay. Another question is, I mentioned optic flow for EAR. Can we use more refined OpenCV functions for optic flow instead of re-implementing it like problem set 4? So in general, I'm always reluctant to say yes or no definitively something is allowed in office hours. In general, the criteria we use for deciding if something is allowed in the final project is it your entire project? So if all you do is call the OpenCV optic flow functions and there's very little else within your algorithm, then no, that's not allowed and you needed to implement something yourself. But if you're using optic flow as one small piece of a much bigger algorithm, for example, you use optic flow and then take those optic flow vectors to determine if something is a plane and then project your image onto the plane and push those into and also use that optic flow within some kind of Kalman filter tracker, then no, we don't require you implement every tiny bit of the project yourself. It's a bit of a sliding scale in that case. Here's an exciting question. For stereo correspondence graph cut, can we talk about how we define a smoothness term? Yeah, gosh, I wish I Wish I had a few moments to type up some equations, but the basic idea, let me pull up my slides, is we want to think about graph cuts as doing some kind of energy minimization. And what on earth does that mean? Well, when we're doing this matching, where we try and find this point and match it with this point, what we're really doing is trying to minimize some kind of energy. So you can imagine if as we slide this window along the epipolar line here, there are varying degrees of matching. And we find the best matching here at this particular point. So we've minimized some cost function. And in simple stereo, the only term in our cost function is how well do these 2 points match. So if we find the point where it's a minimum, regardless of any additional information. And what ends up happening there is when we get our results out, we've got all these little messy areas where something is wildly different from its neighbors. So if we pop back up this example here, where do we get messiness? Well, we get messiness where we don't have strong information or corners or edges to match. For example, the top of this spray bottle, if we jump back to the simple stereo results, is quite messy. So the way you get around that is you have to have something additional in your cost function, not just how well do these two patches of the image match, but also how well does that result fit in with its neighbors. And you can think about that as a smoothness term. So we don't have one in the simple stereo example, and that's why we have these little points in the middle of the image that are vastly different from their neighbors. And so you can think of the smoothness terms as saying things should belong to distinct objects. And that's actually a big part of the idea behind the graph cut algorithms for stereo, is they penalize you in your cost function for having lots of indistinct little blips within an image. It says, in addition to being a good match between the images, you've also got to have firm, distinct edges rather than these little noisy bits within the image. And so that's what a smoothness term is doing. It's a penalty term based on being different from your neighbors within the disparity image. If you look up any of the papers that have been pushed to Piazza, most of them have fairly early on an equation where they'll say, this is the disparity term, and this is the regularization and smoothness term. And you can see how they define those mathematically throughout the paper. Well, lacking additional questions, I'm going to keep talking about smoothness terms and stereo correspondence, because I think it's a fascinating problem, and I'll talk about how it's related to graphs. And this is going to be an example that simplifies things quite a bit. But drawing a picture here, you can imagine representing an image as a bunch of nodes where each pixel is a node. And there are edges between them. So here's a trivial example. We have an image with 9 pixels, and they're connected by edges. And so you can think about this now as being a graph rather than an image. So we've represented our image now as a graph, which is a nice mathematical structure where we have a lot of results. And in particular, we can think about using graph cuts or graphs for segmenting in the following way. We say we connect all of the points to the source and all of the points to the sink, and then we try and find a graph cut that's going to separate the source and the sink using a min-cut algorithm. And the penalty for cutting each link can be cleverly defined in terms of your cost function, such that solving the min flow problem pops out your answer to this global graph cut or this global optimization problem. And we just got 2 more questions in. One is for stereo correspondence. How do we handle image borders? So we don't expect you to do anything magical. You know, if the information's not there because it's off the edge of the image border, then how you handle it doesn't matter so much. Typically, you're just going to want to apply one of the border methods in OpenCV such that your algorithm doesn't break down at the borders. But you don't expect to get great results around the image borders. And I'm just going to throw up slides one more time. These are examples from the simple stereo algorithm, which is not going to give great results. But you can see at the image border here where some of this isn't in the other image, you get very, very bad and somewhat random results. And that's going to happen no matter what kind of edge condition you use. So I guess what I'm really saying is I don't think it matters very much. Pick whichever you think gives the best results, but just use some kind of image border extension for when you're sliding the stereo window near the edge of the image. Another question is, I guess the concept of smoothing and stereo correspondence is like constraining nearby pixels to have the same optical flow in Lucas-Canati in a sense, where we constrain on displacement for a neighborhood. I have to think about that for a bit. You can certainly formulate the problem such that it looks a bit like that, but is it saying pixels in a similar neighborhood should have a similar displacement? But it also goes a little bit farther than that, in that a lot of the graph cut algorithms are minimizing a global optimization problem. So they recognize the need to have edges between images because objects do have edges and there are going to be sharp jumps in the displacement. But you want to minimize those and only have them where they're absolutely necessary. And so it's more than just in Lucas and Canati, we had sort of this neighborhood cloud where we were taking in information from all the pixels in a region. Yeah, so I can, if you want to discuss farther sort of the mathematical similarities and differences, I think we can follow up somewhere where I can write down equations, but I'll also just refer you to the graph cut paper that's been posted a few times. I think the title involves the words graph cuts, fast approximation, and energy minimization, but I'm forgetting the exact order of the words. All right. Another question is, for enhanced augmented reality, would it be acceptable to start with a version that uses all OpenCV library calls and then start replacing those calls with our own implementations? I try not to in office hours say what is and isn't allowed exactly, but Yes, you're certainly welcome to start the project however you'd like. You're likely also going to be able to just keep some functionality in OpenCV calls. As I said earlier, the key determinant for if something is allowed or not allowed is it the core functionality of your project? In particular, if your project is just 10 OpenCV calls in a row, then that's not particularly interesting. It's just chaining together functions. But if you need to use an OpenCV call to do something that's not the core of your project, then you're probably okay to go ahead and do that. And you're also welcome to ask on Piazza, where we can propagate that information more efficiently. All right, I think it's time for me to threaten once again to call office hours early, which always seems to bring in a few more questions. But if it doesn't, we can end in the next minute or two, and everyone can work on their projects instead of sitting here in silence with me. Oh, here's a good question. I just started implementing the SSD version of stereo correspondence. I find that my implementation is really slow. Any tips on speeding things up using linear algebra? I don't think there are any linear algebra specific tricks to speed things up, but there are a lot of NumPy indexing tricks to speed things up. And I'm thinking back to, I've implemented this algorithm a few times, and I believe my implementation ended up building a 3D NumPy array, and then it was just a few NumPy operations and an argmin to pick out the minimums I needed for each point. But in general, if you're having lots of loops, sort of for each pixel in this image, loop over this pixel in the next image, that's a sign you can make things more efficient using some form of NumPy looping or something like that. Or not NumPy looping, but NumPy broadcasting operation. Someone adds for 3D array, it may be too big to fit in RAM for high resolution images. Yes, that's a problem that sometimes happens. It's one of those nuisances with using NumPy, which occasionally encourages you to make very big arrays. There are really two ways to work around that. One is not to do it and just accept that it's going to be slow with the computation. The other is to do batch processing, where you build as big a 3D array as you can handle within the memory you have, process it, and then move on to the next. I'm remembering more about implementing the SSD version of stereo quickly. And so I'll talk a little bit more about that. I think the key idea is that you can imagine you're probably going to have to do at least n big NumPy operations, where n is the width of your image, the length of an epipolar line. But you can imagine doing all of the pixels at once for each displacement. So you'll end up building an array that has dimensions, number of pixels by the maximum displacement you're willing to consider. And then you just take an argmin along that backwards axis. So you can imagine sort of having one image and then slowly shifting it to the side, and you can sum up around your little window just using a normal filtering operation. Sort of that's the big high-level picture in words of how to perform this operation quickly without with only one sort of loop over the displacement axis. Also, if you're running into memory problems with the sum square difference stereo algorithm, another thing you can do is you can manually look and say, okay, what's the max displacement I see in this data set? Like, what's the maximum distance something moves? And then rather than calculating all possible displacements, only calculate up to the max possible displacement. Also, for optimizing memory use, you can pick some displacement stride and look, say, only at displacement of every 2 pixels rather than every pixel, and that's going to half the size of your array. And then you might want to do something iteratively after you do that to fill in the missing resolution. I'm just thinking out loud here. One of my favorite things to do is optimize code for sort of speed and memory use. If anyone else enjoys that sort of making code run very, very fast and thinking about memory layout, I highly, highly recommend Introduction to High Performance Computing, which I'm taking this semester and has been one of the most intense and also fun classes I've taken in the program. All right, it's been, I'd say, about 8 minutes without new questions, and I'm starting to talk on random topics and give course recommendations, and this whole office hours is falling apart. So, there's another question. The secret to getting questions is to make it sound like I'm going to end office hours. So the question that just came in is, for our presentation in the end, how much detail do we need to cover? The workflow for our code, or just how accurate it is, like prediction? I think I'm going to punt this question and ask you to make a Piazza post on the topic. I have in my mind a very clear image of what I think those presentations should include, but I haven't discussed it in great detail with the other TAs. So I'd like to avoid giving you bad information here and only have to rescind it once I get back and chat with the rest of the team. The questions are getting very meta. The one that just rolled in is there a list of questions asked earlier? I joined late and just got off of work. So not in any simple form. I've gone through all of the questions that were posted on Piazza prior to office hours starting. And then just very quick summary. I've answered a number of questions about stereo correspondence and the SSD technique and some of what that means. And I've also answered some questions about enhanced augmented reality. I try pretty hard to repeat questions whenever they're asked. So if you skim through the replay on high speed, you'll be able to hear me repeat questions in a squeaky voice. And also see what was addressed. I'm not sure I have a better answer than that for you. Question, how successful are past students' final projects, publishable? This is the first semester we're having a final project in computer vision. In past semesters, there have been 2 extra problem sets instead of the project. But the same professor who does computer vision, Professor Essa, also does computational photography. And there have been some very excellent final projects that have come out of that class. I'm not sure if anything has been publishable. I don't think so, but we'd certainly be happy if you were the first. Hmm. Okay, everyone, we have 2 minutes left. And so if you have any last minute questions that are very important, now is the time to ask. Do not delay. All right, so I'm seeing no additional questions. I want to address 2 points before signing off. One is I expect that many of you will start getting intermediate results or initial results from your algorithms and projects in the near future. You should feel free to, if you've got something cool to show, post that on the Piazza discussion page related to your project. Don't share code, but it's fine to share, here's a video of what I'm getting now. We, the TA, the teaching staff, are very curious to see how people are progressing. And I imagine your classmates would also be interested to see what kind of results you're getting. So I want to just use a minute here to encourage posting intermediate results and cool videos, cool imagery you're generating through your projects. The other thing I wanted to say is thank you, everyone, for attending these office hours throughout the semester. It's been one of the highlights of TAing. There are no office hours next week, the day before Thanksgiving, but we will have one last office hours, which will be, I hope, some kind of total course review to get ready for the final exam. So with that, good night, good luck, do something amazing for the final project.